Hello everyone. Thanks a lot for being here, especially when the other track is having a session on AI, the buzzword these days. So yeah, thank you for showing up. So as you all know, the topic of my discussion is Incremental Materialized View 101. Quick introduction of me, I'm Tushar Amrit and I work with Bloomberg as a software developer, and I identify myself as a database enthusiast. Just a quick request, I'll be having a Q&A session in the very end, so hold on to your question till the end of the session. Hopefully you'll get to learn something new about Materialized View today. So just like any other wannabe engaging speaker, I'll begin my talk with, imagine this. So, okay, I guess the slide is not working. Speaker, I'll begin my speech with, imagine this. So imagine this, you worked hard and created a query that draws insights from the vast database that you're working on, and the results that you are generating is profoundly important for the company, the query, and in order to add cherry on the cake, you use Materialized View in order to optimize the query, and now your query runs in a blink of a second. But then the inevitable happens. The data underlying your Materialized View gets updated, and all the results that were drawn, all the analytics that were generated is now irrelevant. And this is because the data which was used to create this analytics was stale. So what to do in this situation? This is what I'm going to try to answer in this talk, where we will go deep dive into the world of Materialized View of Postgres and try to find out the best way of data refreshing so that our query time is not impacted. So the agenda of the talk is understanding Materialized View and why do we really need them. We'll try to understand the issues that we face with the traditional implementation of Materialized Views in Postgres. Then we'll find the solution in the extension of Postgres, which is PGIVM. And then we'll deep dive into understanding the internals of how PGIVM works. So let's start from views, because this is Incremental Materialized View 101. So I'll begin from the very basic and then deep dive into updating our views incrementally. So views are nothing but virtual tables that are used for simplifying queries. In other words, we can say views provides us the ability to query on the result of another query set. Thus it provides a sort of abstraction for complex queries. And by complex queries, there can be queries that contains a lot of joins, operation, where clauses, and having a group by clauses and whatnot. So views are also used for optimizing performance. This is what we are going to see today. So in order to give an hands-on experience on how we are optimizing our query, I'll be using this sample schema, which is quite straightforward, to show how we are optimizing our query step by step. So this schema is quite straightforward. It has three tables: the order table, the user table, the product table, and the order table. As their name suggests, the user table provides the detail of the user, product table has the details of the product, out of which the most important is the price of the product. The order table has the quantity of a product, what a particular user has bought, and we have set up indexes on our tables. So since we want a large data so that we can optimize our query, I have used the Faker library of Python using a script whose link I have attached in the PPT. You can find it later after you get the PPT slides, and use the scikop-g2 Postgres adapter in order to add the data to our Postgres database. We have added 11 million rows in the user table, 11 million rows in the product table, and 4.5 million rows in the order table. So the query that we are going to optimize today is to the calculating the total amount ordered by a particular user. Not a particular user, but actually all the users that are present in our database. So this query requires join from all the three tables, because the price of the product is present in our product table and the quantity of the product that a user ordered is present in our order table. Then we use this sum aggregate function to get the price, get the order amount for a user, and then we aggregate it using sum. Since this is quite complex query, you can see that it is taking 26 seconds to execute. And this is the result set, some rows of the result set that was generated. It has a user ID, username, email, and total order amount. So now we apply views in our query. This is not an optimization, it's just creating an alias for the query that we were using. and you can see the creation of view didn't take much time, it's just 98 millisecond, and the query where we refer the view that we created is taking 28 seconds. This is because it is doing again the same computation that it was doing in the vanilla SQL that we saw before. So how do we optimize this? For optimizing our query, now we are going to materialize our view. And what do we mean by materialization is what we'll see in the next slide. So materialization is nothing but pre-computing our result to improve our query performance. We can consider it as a sort of adding a cache layer in our database where we know that we're going to get this particular query, so we pre-compute the results and store it in another database object. So, and whenever we want to use that query, we don't go and directly compute everything right from scratch, but we use the data that we have stored already. And this is stored persistently in our database. But again, since we are storing our result in another place, there can be a case when our base tables or the original data that we were working on gets updated. And when it gets updated, we reach a state which is inconsistent. Our data of materialized view is not consistent with the data present in our base tables. So for that, we have a solution of refresh, which is on-demand refresh, in order to get the real-time accuracy. This approach is really great for optimizing read-heavy workloads because we are optimizing the reads, and we have already pre-computed everything and we don't have to compute it again when we get the read operation. Another feature of materialized view is that it can be indexed. So we can create index on the columns that basically didn't exist in our base tables. There is no support for temporary materialized view. By this we mean we have to create the materialized view before we going to use it in our query, and we can't drop it once the query is over. So we have to explicitly do a create operation and then we have to do a drop operation. This feature is supported in Postgres since Postgres 9.3 version, which came out in year 2013. So where does materialized view comes into picture during query execution? So it comes into picture when in the rewrite phase, which happens after the parsing of the Postgres SQL query and before we start planning for our execution. This is sort of a user-defined rule that we tell the Postgres SQL that whenever this particular query comes up, use this particular database object. So how do we implement materialized view in Postgres is covered in this slide. We basically use the create materialized view command query in order to create our materialized view. We can see that it takes a number of tunable parameters so that we can get the perfect materialized view that we want. Out of which the most important is the last one, which is with data or with no data. By default, if we don't mention anything, the materialized view is created with data parameter, in which mode whenever we complete the execution of this query, our materialized view is not only created but also populated with the pre-computed computed result. Whenever we run our query with no data mode, then only the metadata for the materialized view is created, and it gets populated only when it is first referred in another query. So now let's create the materialized view for the query that we were optimizing. So here you can see that we are using create materialized view command, and now we have created a materialized view whose name is user order summary MV. And this query again takes 26 seconds. But now it's important to mention that this is only a one-time query. We don't have to do this computation again and again. Our data is stored in the materialized view whose name is user order summary. We can also add indexes on our materialized view, as you can see in the bottom section. So now we have computed our result, but we want to get the same result set that we were getting from our vanilla SQL. So for that we do a select star command, and you can see this is now taking only 2 seconds. So this is nearly 10 times reduction in the execution time. So yeah, we can see that this is a very great sort of optimization that we are doing over here. But since it do also have some trade-offs. The first one, what we're going to see is the refresh. Now, as I mentioned before, it can, since we are storing our data in another place, it can lead us to the state of inconsistency where our results are not consistent with our base table. For that, we do a refresh materialized view command in which again it takes the with no data parameter And again, we have a new mode where we can refresh our materialized view concurrently. What this particular command does is basically it does a hard refresh and a complete refresh. From hard and complete refresh, I mean we recalculate all the data points that we had in the materialized view right from the scratch. If we run this query without the concurrently parameter, then we also have locks in our materialized view. So at that time, we can't access our view data as well. But when we run it in the concurrently mode, then we can access our view at the time of refresh. This is because when in this particular mode, the PostgreSQL creates a new materialized view. It populates it right from scratch and then rename it with the materialized view name that we had provided. So again, we are adding another layer of computation. So let's try this on our database. We first update our order table by just setting a value of quantity to 10 for a particular user order ID. And you can see the update is quite fast because we have already set up index on order ID column. But now when we refresh our view, we see that it is again taking the same magnitude of time that it was taking for computing everything for displaying, or when it was or the time that it was taking for creating the materialized view. So now what we have done, that we have made a trade-off between the read and write. Not exactly write, but whenever you want to get the updated version of the data written in our database. So summarizing the issues that we have with our traditional implementation of materialized view, first is the maintenance overhead. So we have to manually go and tell Postgres that we want to update our materialized view, go and do a hard refresh. Another problem is the computational heavy approach that Postgres follows, that it completely do a hard refresh and calculate all the data point right from scratch. And when we are doing it concurrently, we are adding another layer of computation. And locks during refresh is what we face when we don't use the concurrently mode. So now we have problems, so let's try to find out the solution. And the solution for this problem is to incrementally maintain our materialized view. Before explaining what does this mean, let's think of approaches that we can follow to maintain our views. There can be basically two approaches that we can follow. One is the immediate update, another is the deferred update. By immediate update, I mean whenever we are updating our database, the base tables, we in the same transaction go and update our materialized view so that atomicity is maintained. The deferred update means the one that we have been talking till now, that we manually go and do the refresh whenever some data has been changed in our base tables. And again, this deferred update refresh leads us to stale data, and again, there is no atomicity guaranteed. So by incrementally maintaining views, we mean that we only update the rows that were affected in our base table. So for every rows in base table, we have some corresponding rows in our materialized view. So instead of recomputing everything, we only update the table, the rows that are corresponding to the rows that were affected in our base table, and we do that automatically. So this is the gist of incrementally maintaining our views. So in order to understand how we can do that, let's deep dive into some algebra. So in the bottom left corner, you can see we have the base relation. This represents the base table that we have, like the user, product, and order table that was in our example. We apply our view definition on the base relation, and we get our materialized view. Now the base relation undergoes an update through an update query u. And we can represent the changes that were made in the base table as delta b. Now we have the updated base relation, which is b dash. And right now what we are doing is doing a recomputation on the base table in order to get the mv dash, which is the updated materialized view. But this is not the case in incrementally maintaining materialized view. In incrementally maintaining materialized view, what we do is we basically try to propagate the changes that were made in the base table in order to extract the changes that are required to be applied on our materialized view in order to get the updated state of materialized view. So here I am denoting the materialized view as IMV, which stands for incremental materialized view. And we are getting the updated version of IMV, which is IMV dash, by just applying the changes in our IMV. Now this approach seems correct, but how are we going to propagate the changes? So for that, let's take an example of natural join. Let's consider for this example, the view definition that we are talking about is quite simple as A natural join on B, where A and B are our base table. And now our base table A undergoes some changes. The changes can be represented by some rows that were added and some rows that were deleted. In any, if we consider an update in a row, we can consider it as the deletion of the row and then addition of the same row with the updated value. So now let's take the delta rows as the rows that are added in this update operation, and the gradient rows are as the rows that were deleted in this operation. So now we can represent the updated state of our base table A as same as union of our delta A with the initial version of our table A minus the rows that are deleted, basically the gradient A. So now in order to get the tuple that are needed to be deleted in our view and the tuples that are needed to be inserted in our view, what we can do is that we can apply the view definition with the base table replaced with our delta and gradient rows. So here we can see we can get our gradient row in V by just taking the natural join of gradient A with base table B, and we can get our delta rows in V by taking the natural join of our delta A with the base table B. Applying these changes in our view, now we get the updated state of our view as view is same as the delta V with union of delta V with the initial version of delta V, without the gradient V. So yeah, now we get the basic theory of how we are going to propagate our changes in our materialized view. But how are we going to get the rows that are basically delta A and gradient A, which is basically the rows that are needed, rows that were added in our base table and rows that were deleted from our base table. So basically we have two approaches for getting these rows. First one is using triggers and transition table. This is the approach that we are going to follow in our slides. I'll be talking more about this in the upcoming slides. And another approach for getting these updated rows is by logical decoding of the write ahead log. For people who don't know about logical decoding, it's a feature of Postgres that was introduced in Postgres 9.4 in the year 2014, where we can basically decode the write ahead log and get the rows that are affected during a particular operation. So that is a second approach. Okay, so now we have the idea of how we are going to update our materialized view incrementally, and we have some approaches that we can follow. So now what we can do is like just go to our database, write some triggers, or just start logically decoding our write ahead logs and do every stuff to update our views incrementally. But what if I say that everything that I'm talking about is already implemented, and it is implemented in the Postgres extension PGIVM, which is the savior for us. So this extension was released by IVM development group led by Hugo Nagata. I'm really thankful to Hugo for helping me make this slide deck as well. So he led the IVM development group for this extension. This was first released in the year 2022 in the month of April, and it's compatible for Postgres version 13 and above. So what this extension basically does is that instead of us going and running refresh every time whenever there is change in the base table, it automatically and incrementally updates our materialized view so that everything comes into the consistent state. So how do we use this extension? We basically have to download the source code with the link provided and then execute the make install command in our database. And then we create the extension using the create extension. By installing PGIVM, what happens in the backend is that three main functions are installed in our database. The three main functions are create IMMV, refresh IMMV, and get IMMV definition functions. As their name suggests, they are used for creating materialized views, refreshing materialized views, and getting the definition of the materialized view. So let's create the materialized view for our database. So we can use the create IMMV command. So IMMV stands for incrementally maintainable materialized view, but I'll be using the term IVM because IMMV is mouthful. So I'll be using IVM for further slides. So we use the create IMMV function which takes in parameters the name of the materialized view that we want to create, and the query that is required for creating this view. This is quite equivalent to the create materialized view standard command that Postgres support. So now we are creating the IVM for the query that we are optimizing. So we now create the IVM whose name is user order summary IVM, and we use again the same query that we have been using so far. And you can see this is taking 48 seconds, which is about twice the time that our materialized view creation or refreshing was taking. The reason for this is because PGIVM does a lot of computation in the backend. It adds some columns in our materialized view in order to maintain it automatically. But again, it is a one-time cost that we have to face for creating the materialized view, and then we don't have to worry about the updation. So now let's update our base table and see how it performs. So yeah, before that, we can try to get the same result set that we are getting from our vanilla SQL, and we can see again this is taking 2 seconds, which is similar to the time that was taken by materialized views. Now when we update our base table, we see that it is taking quite some more time than the normal traditional materialized view updation was taking. The reason for this is again in the same transaction as the update, now we are updating our views as well, because of which there is slight latency. So now let's deep dive into understanding how PGIVM basically works. So it uses the approach of triggers and transition table. To be precise, it uses after triggers, which are statement level triggers that are used in this approach, where we get the delta and the gradient rows using the transition table. The transition table was introduced in Postgres 10. They are also known as the pseudo table, in which basically whenever an operation takes place using a trigger, we can get the rows that were added or the rows that were deleted using the new and old keyword within the trigger function. Let's see an example in the next slide. Here we can see that we are using the transition table in the second query, and we are basically the new table, the new underscore table underscore a now denotes the delta a that we were talking about in our before slides. So now we have the rows that were affected, and now in order to get the rows that we want to apply in our view, we rewrite the view definition and get the delta v and delta and the gradient v that we are going to apply on our view in order to update it. So this is how basically the working of the normal use case of PGIVM works, but there can be some edge cases, and let's talk about some of them. So how we are going to handle the duplicate rows for distinct clause. So there can be a case when when our view definition has the distinct clause, but the base table has duplicate rows. So we can't just directly go and delete the rows that were affected during the updates. We have to keep in mind if, for example, if we take the second example provided in the slide, if we are deleting the tuples from the base table and they were duplicate and our view had distinct clause, we can't just delete all the row from our view, because it may happen that there are rows that are left with the same data, but they were not affected during the update operation. So we have to maintain sort of a count, and whenever the count turns to 0, only then we do update our view. So for this, PGIVM used the counting algorithm. So by counting algorithm, what PGIVM does is that it introduces a special column in our materialized view, which is known as the underscore IVM count underscore, which maintains the count of every tuple that are inserted in our view. Whenever we are adding a tuple in our view, we not directly add it in our view. We check whether the initial count of that particular row was 0 or not, and if it was 0, only then we add it. And similarly, in the delete case, we delete the row from our materialized view only when the count of the row turns to 0. This is an example of how IVM count works. On the right hand corner, you can see the column that contains the count of each rows present in our materialized view. Another edge case of PGIVM that we can discuss is handling of aggregate functions. So PGIVM does support all the built-in aggregate functions, and whenever there is update made on the rows, what PGIVM does is that it only applies the aggregate function on the rows that were affected, gets the result, and then apply the update to our view. But this update method varies for every type of aggregation. Apart from that, we also add some special columns present in our materialized view in order to make the computation easier. For example, if we have the average aggregation function in our view definition, then we add the columns of sum and count so that it's easy to calculate the average. Now let's talk about concurrent execution. So what if multiple queries are trying to update the same row in our materialized view? So how PGIVM works for this is it obtains exclusive lock on our materialized view, and if the isolation level is set to the default of Postgres, which is read committed, then the second query that is trying to update gets slowed. So it has to wait for the completion of the query of completion of the first query, only then it makes the changes for that particular row. But if the isolation level is set for repeatable read or any other higher isolation level, then the second transaction gets aborted. So this is a caveat in the implementation of PGIVM. But again, it's not the only caveat. We do have some more problems in PGIVM. So first of all is the loss of performance in the update of base table. As we saw in one of the example, that the update does take some more time than the usual traditional materialized view update because of the updation of the view in the same transaction. Another issue with PGIVM is it only supports the built-in aggregate functions. The reason for that, whenever we create a user-defined aggregate functions, PGIVM doesn't know how to update the rows after getting the value of the delta. Right now, only the inner join and the self join are supported, but there is no support for outer join in the view definition. Our base tables need to be simple in order to use, if we want to use them in the query definition of PGIVM. They can't be another view, or they can't be foreign data wrapper or anything like that. The logical replication is not supported. So now if we want to support logical replication in our database which uses PGIVM, we have to handle it on ourselves. So I guess, yeah, it brings us to the end of our slide deck where we draw conclusion of the PGIVM extension. So yeah, PGIVM is a great extension to use, but it comes with great drawbacks. And I guess the most suitable situation where we should use PGIVM is when our table is not updated that often, but we want the latest updated state in our materialized view. Apart from that, a best use case can be if we are doing a lot of update in our base table. What we can do for some time is we can pause the automatic update from PGIVM and then update our base table, and then again create a new PGIVM IMV in order to get the updated version. So yeah, I guess that brings us to the end of the slides, and I'm open to take up any questions that you have.
So I'm actually finding it quite amazing or even unbelievable, because SQL query can be arbitrarily complex, right? You can have you can have cities.
Yeah.
So not just aggregates, right? You can have aggregates, or you can do a lot of stuff with aggregates. You can have multiple cities. How can that plugin ever keep track of everything?
So yeah, so right now this plugin basically works on simple queries. We can try out different queries with CTs and all, and try if PGIVM works or not. But as I mentioned, there are many caveats where it doesn't support complex queries, where we use some user-defined aggregate functions.
So in those cases, does it give an error?
Yeah, it does give an error that this is not supported in PGIVM.
And also there are some queries, right, where even a small change in the input causes a lot of change in the output.
Yeah. So if an update is making changes to multiple tables,
let's take the example of maybe rank. Suppose you calculate the rank, right?
Yeah.
Now you have 1 million rows and you have a rank of all of them. Now suddenly someone comes with rank 1. You literally have to update the rank of all of them.
Yeah, so again, that update will be slower than the update that we do in natural materialized view. But again, it will be in the same consistent state with the base table and the materialized view.
So effectively, every update will become almost like a full refresh.
Not full refresh. If the update is making changes to all the rows, then it will definitely make update in the whole materialized view.
So in that case, the limitations are not just self-charge, but much more, right? The limitations. I'm not sure what is the limitation, but I just can't imagine it handling CTs.
Yeah.
Does it handle CTs?
Right now, yeah, it does handle simple CTs, but complex CTs are not supported.
You talked about this transition tables.
Yeah.
So this is like a transition table per table in the join, or it's one table, one transition table per view, materialized view.
It's like for every table, different.
Every table which constitutes the
view. It gets the rows affected of every table that were involved in that update operation.
Right, and one transition table per
table.
Per table.
Yes.
Okay. And I mean, I'm just thinking, on transition table also, can you face contention or no? Not contention.
What type of contentions?
Can there be contention on the transition table updates or inserts also with the triggers?
I don't think so. We haven't faced anything like that right now.
Okay.
But yeah,
Okay.
think like food to thought. Yeah.
Okay, I think that clears my doubt. Thank you.
Thank you.
So on the contention issue, I have seen tables getting locked up when updates are used with triggers. So have you seen anything like that?
Yeah. So as I mentioned that it does do an exclusive lock. So until the updated or the trigger function is completed, there is lock in our table.
So if you have like lots of update traffic, you're basically shifting the delay of the refresh to the update.
Exactly. Yeah, exactly. This is what PGIVM does. It shift instead of us waiting for refresh, we have to now wait for update. But now again, that's the trade-off that we are facing.
Depending on the kind of application, it might be a bad idea.
Correct. So it's like if our updates are not that much and we are only updating some rows, then this is a great solution for our database.
Storage.
So yeah.
Hey, does the extension add triggers to all the tables that are part of the query?
Yeah, so all the tables that are in view definition.
And are these row triggers or statement triggers?
They are statement triggers.
Statement triggers.
Yeah.
And what happens to cases where, say, you're going to update all the rows, multiple rows? So calculating, you're basically calculating a lot on the update queries itself. So I understand it's a trade-off.
Yeah.
But it also depends on, so for example, if you have triggers on the next table also, does it mean it will calculate all the things then?
If it's the part of the same update function, then it will also have some triggers. The second table will also have triggers.
And can you talk about the use case that you solved using this extension? Why did it work for you?
So yeah, I guess the best use case that I mentioned also in the conclusion is that whenever our table is not updated that often, but we need to have like the result updated in the real time. So this is the use case that is best for this extension.
Hi. The algebra is very elegant. So could you go back to the query that you were showing? The order summary?
Yeah.
Yes. So you say that you maintain IBM count as the metadata in it, but now we have sum, but if we change it to a different aggregate function, like say mean, right? So how exactly does the recomputation happen? I understand that we do have the metadata, the total count, so we can recompute the mean, but isn't the mean aggregate something which the PG query execution executes? So how does that link up together?
Like if I understood your question, first like instead of sum we are using mean in this query.
Exactly, replace it with mean.
Yeah, so for mean we like add two columns. One is the sum and another is the count. So count is, as I created, like IVM count is the column that maintains the count, and for some, again, we have to like do the same stuff that we are doing over here.
So even if there are like updates or deletes which happen into the table, we need to recompute for all the order IDs, right?
Only the affected order IDs, right?
Because you have an existing mean and the count changes, and you only have the values in it, right? So you cannot take an existing mean and a new mean and get a new mean. That would be a very wrong mean, right? So
Yeah, I guess it depends upon the how the use case of average is. If it's average on the whole table, yeah, then it definitely we have to do the computation on the all the rows that are. Yeah,
got it.
So I guess so I guess since there are no more questions, we can wrap this session up. So thank you.
Yeah, thank you. Progress equal